Today we're going to talk about arc length. We discussed it at the very end yesterday. And then after we get through arc length, we'll do some more examples of areas. Okay, so let's recall this motivating picture yesterday. You have some function f of x. We choose 2 points, A and B. Of course, we always have our standing assumptions that f is sufficiently nice to make everything work, so usually continuous, possibly differentiable. For in this case, we're going to want differentiable. Okay, and so we have this nice curve, and before, of course, we computed the area under the curve above the x-axis. Now we forget about that, and we say we just want to know the length, right, of this line in between. So if we pinched the endpoint and it was a piece of wire, you could go stretch it out, and then you could use a ruler and do it, and that would be the easiest way. Unfortunately, this isn't a wire. We don't have this. We don't have a piece of wire even to cover it up with, so we want to try to do this analytically. Okay, and the idea that we had yesterday was we'll start drawing points right, in between here. And then connect the dots with lines, straight lines. It's not very good. You can already see that with just actually a few dots on here, we did a pretty good job of approximating this curve with just straight lines. Right? Okay, and so then what we would want to do is just compute the length of each of these line segments and add them up. So let me give names to these points. So since they're points, I'll use the letter P. So I'll call that P0, and this will be P1, and that'll be P2, and P3, and P4, and P5, and P6, and this will be P7. Yeah? Okay, so if I say that the, let me say the length, I'll use a capital L for length. And then I'll put down here the interval a to b. And don't worry about this notation, because we'll get rid of it very soon. Okay, so the length on the interval a, b of the function f equals, all right, well, we don't really want equals. We want is approximately equal to the sum of the length of these line segments. Okay, and so, you know, geometry, sometimes if you have a line, you write the 2 points on the line, A, B, and then put a bar over it to say you have a line or a line segment. Right? Okay, and then if I put these, what look like absolute values around it, just says what's the length. Right? Okay, and then I just need to tell you what the bounds are. So I started with 0, and I go all the way up, to, in this case, to 6. Wow. Okay. Simple enough, yeah? Nothing too complicated. And if I did this again with more points, then, well, nothing in here would change except for the number of points I have, right? Which is, in this case, I have the 7 points, right? So I could just go up to some n. So for any n, this will give me some nice approximation. And if I actually want to get the actual length, right, equal, what am I going to have to do to this n? Yeah, you want there to be an infinite number of points somehow, yeah? So you take the limit. Okay, so right, this length should equal the limit as n goes to infinity of the sum I equals 0 to n, right, of the length of these line segments. fine, except we don't know how to actually compute this limit. Right? I mean, it's there, but okay, that could be annoying. So we need some more information. So let's look at this bit. Right? We can say a little bit more about this. So let's say I have 2 points, and I'll draw them far apart here just for clarity. Okay, but normally, of course, these are always close. So this could be my pi, and this would be pi plus 1. All right, now, let me make a simplifying assumption. Bless you. An assumption that doesn't, it really won't hurt anything. And we could have done this, actually, when we did the area problem. Just a nice simplifying assumption. I always said you could just take partitions of A to B. Right? I mean, we just take partitions when we did the area problem. And that the distance between, right, the points in your partition, that could be anything you like, right? You didn't have to make it even. Let me just, for now, just assume that these are equally spaced. Right? So they're equally spaced. Okay, fine. So I have a line segment between pi and pi plus 1. And, well, if we view this all sitting in the xy plane, there are coordinates of these points. So this might be xi comma yi, and this could be xi plus 1 comma yi plus 1. Okay, so what is the length of the line segment pi to pi plus 1? What formula do we have to use? Yeah, you can actually, when you say Pythagorean theorem, that's exactly the genesis of the formula, which is called exactly the distance formula. Right? But the Pythagorean theorem is really what's giving it to you. Okay. So it's equal to, right? Well, it's, if you like, you can draw the x line and a y line, and then this is the hypotenuse of that right triangle. So you know it's going to be the square root of, well, xi plus 1 minus xi squared plus yi plus 1 minus yi squared. Okay. Now, we said that we were making this simplifying assumption. Oh, Dina, yeah? Is this a proof of what? We haven't. It's not a proof so much as a derivation. We're actually trying to figure out what the arc length is. We don't know what it is yet. I haven't suggested anything, so I can't prove it. Okay. So we said that I was going to equally space these p0s to p1s. Now, actually, what I said probably was wrong. I said that I wanted these line segments to be the same length. Actually, I don't want that so much as I want the x. If we had partitioned A to B again, I want those distances to be the same. So that xi plus 1 minus xi is always the same number. So let me just call this delta x. And I don't need to put a subscript because it's always going to be the same number. Okay. I don't have to do that. It just simplifies things. Okay. And then let me call yi plus 1 minus yi delta yi. And there I do have a subscript, right? Because that depends, right? I may be able to fix this horizontal distance, but the vertical distance can change. Okay, so that's delta x, and this is delta y0. Okay. So at this point, I can rewrite as delta x squared plus delta yi squared. And, well, I play just a little algebra trick here. Let me factor out a delta x squared. If I do that, it looks like this. Okay? You can think I can just put this back in, right? And it would cancel this thing I introduced on the bottom. Okay, why am I doing that? Well, I want to pull this delta x actually outside. Why do I want to do that? Well, when we computed the area under a curve, remember what the limit looked like. You had the limit, then went to infinity, you had a sum, then you had the function evaluated at a point times delta x. Right? That was the width of the rectangles. Right? Height was the f evaluated at a point, the width was the delta x. Right? I'm trying to mimic that format. Right? I'm trying to mimic it, so I want to get a delta x out by itself. So I rewrite this as the square root of 1 plus delta yi squared over delta x squared. Right? Of course, I could actually pull the parentheses out and just square everything at once. And then if I break this up as the square root of this times the square root of that, but it kills the square. Right? And since delta x is positive, I don't worry about taking the negative square root. Okay, so we now have a different interpretation of this length, which allows me to rewrite this expression. Okay, so the length of f on the interval AB should equal the limit as n goes to infinity, the sum I equals 0 to n. And now instead of having this just the length from pi to pi plus 1, I can write down the square root of 1 plus delta y I over delta x squared, and then on the outside times dx. Okay, now, here's the fun part. As n goes to infinity, what's happening to the terms here? They're what? They're well, let's see. What's happening to delta x? Gets smaller, right? As the number of points increases, then the width between those points has to decrease. Okay? And what about the height difference, right? As you move these, as you get more and more points, how much can it go up from point to point? All right? If I put more points in here, the y value has to get really tiny, right, as you go up. I mean, the difference in y values gets really tiny. So both of these are getting really, really small. So, okay, so have we ever seen something like this before? Or effectively, right, we can view delta x going to 0, delta y over delta x. Right? Of course, delta y is also going to 0 here too. But not exactly in the same way as x, because y is dependent on x. We've seen this before. We spent a lot of time with it last term. We didn't usually write it down in this way. But it's effectively the same thing as we did. This is the derivative. Right? This is f prime of x. Right? Think about what's happening here. You're looking at what happens when you change the y value over increasingly smaller changes of x, right? But what's the relation between changing the x value and changing the y value? Well, that's a slope, right? That's rate of change of y with respect to a change in x. Right? And the derivative is what happens is you take the rate of change of x and let it go to 0. Okay? So we're actually just get dy dx here. So this under the radical just goes to the derivative of x. Right? This is just f prime, or dy dx. Okay? So now you have a function, the square root of 1 plus dy dx squared times delta x. So you have a limit as n goes to infinity, sum I equals 0 to infinity, from 0 to n rather, right, of a function times delta x. That is exactly the definition of the definite integral. Right? Remember our definite integral, you had some function. Let me use a different function name. Let me call it g. This was, by definition, the limit as n went to infinity. Okay, we also said something about delta x, but we'll make the simplifying assumption here. All right, of a sum, I equals 0 to n, g, well, you had some points that you looked at, times delta x. Okay, that was our definition. Right? You can look it up in your notes. This is how we define the integral of g of x. Right? Well, we have the exact same format here. Here's our new function, right? There's our function. That's our g. Okay, times delta x. So we can write this as the integral from a to b of the square root of 1 plus dy dx squared dx. And so this is the arc length formula. Okay. It's okay if this is not easy. Some things aren't. Okay. And let's do an example how to use it, but it's actually just now a computational problem. So let's look at x to the 3 halves. Okay, that's a nice reasonable function. And let's compute the arc length between, say, 0 and 5. So by what we just proved, the arc length is going to be the integral from 0 to 5, the square root of 1 plus, well, the derivative. Okay, so what's the derivative of x to the 3 halves? Let's write it down up here. Ah, yes, derivatives are so nice. You hardly have to think, right? Okay, so I need to do 3 halves x to the 1 half. But it's not just the derivative. I have to do the derivative squared. And then dx. Okay, so now it's just fiddling with this thing. Let's see. If you square 3 halves x to the 1 half, the 3 halves becomes a 9/4. And the x to the 1 half, when you square it, just becomes x. And I would guess Shirley knows what to do to evaluate this integral. You did 100 of those things. You don't have an idea what to do? Okay. What do we do? Okay, if you like. I can't stop you from doing that. Okay. What's a good idea for this integral? Ah, u substitution. What's your u? Okay, let's try it. U equals 1 plus 9/4 x. So what's du? 9/4 dx. Okay. So then dx is du times 4/9. So I'll just have to whip a 4/9 outside. All right, so this is just going to end up being u to the 1/2. All right. There's actually a point we need to talk about a little later on, which is when you're evaluating a definite integral and you do a u substitution, how that affects your limits of integration. So you have two choices. You can either change the limits of your integration, or you can work the indefinite integral externally, right, on the side, and then write down the answer using but put it back into x's, and then use your original limits of integration. Right? So let's do it that second way for now, right, where, okay, this became u to the 1/2. So then the antiderivative is, what is that going to be? You have to have 1, that's 3/2. Then you divide by 3/2, which is 2/3, right? So you get 2/3 u to the 3/2, but u is 1 plus 9/4 x. Right? And then we have to evaluate this thing at 0 and 5. Okay, so now this is just plugging things in. So let me write down. I won't work out all the arithmetic since what's the point? Okay, but we can at least plug it in. All right, so first, well, okay, I can easily see this. That's going to be 8 over 27. And that I can pull out of everything. And then, okay, when I put in a 5, well, okay, it doesn't look great. I get 45 over 4 plus 1, which is 49 over 4. To the 3/2. And then you have to subtract, right? What happens when you plug in 0? When you plug in 0, you just get 1 to the 3/2, so it's 1. Okay, so up to any arithmetic mistakes we've made, that's what you get. Right. You can actually do something with this, right? Because it's easy to take the square root of 49/4. You get 7/2, and then you cube it, and you get 343 over, well, did I say 4 over 7/2? 343 over 8. I guess I'll write that, as long as I'm here. I can't help myself. So you get 343 over 8 minus 1 is, we have to subtract 8 from 343, so you get 335. Was it 16? Let's see, if we square root, you get 2, cube it, you get 8. Yeah. Okay. And then, oh, the 8's cancel. That's really nice. Look at that. I just can't help myself. Arithmetic is fun. Okay. Good, good, good. Okay, so that's how you find the arc length. So when you put a 0 in here, you get 9/4 times 0, which is 0, plus 1 to the 3/2. Of course, 1 of the 3/2 is 1. And then this stuff was just on the outside. This one? So remember, we made this substitution. So you're integrating u to the 1/2. Right? And so the integral of u to the 1/2 is 2/3 u to the 3/2. So that's where that 2/3 comes from. All right, 49 over 4. Take the square root. You get 7 over. No, it's 343. But then so you have 343 over 8, but then you have to subtract 1, or 8 over 8. And so you get 335 over 8. Well, what I did is I first multiplied these. And I got 8/27. Right? And I know that I just pull it, I just factor it out. Right? Yeah. Always, whenever you can, whenever you're evaluating these limits, it's good to factor out as much as possible so that you don't have to do as many computations. The more computations you do, the more likely you are to make an error. So, I mean, odds are I'm wrong. We did too many computations for me to be right. But we'll let somebody, one of our viewers at home, please send in the correct answer. Okay, let me see. Get our time check here. Okay, good. All right, let me just push this a little bit further. Just a little bit further. Wow. Oh, there's my eraser. So I want to relate this a little bit back to the fundamental theorem of calculus. And when I say that, I mean f-talk 1, not f-talk 2. Of course, we already used f-talk 2 to evaluate this thing. But I want f-talk 1. And remember what f-talk 1 said is if you write down a function and then you integrate it from a to x, and you let x vary. Right? So it was the moving the sheet off the transparency, right? Then you get a new function, right, of x. And if you differentiate that function, you get back your original f. That was what f-talk 1 said, right? It had if g of x equals the integral from a to x of f of t dt, right, then g prime, let's write like this, g prime equals f. Okay? With sufficient conditions to make this all make sense. Okay, that was f-talk 1. Okay, so I want to try something similar with arc length. And what I mean by that is I want to make a function which is sometimes called s of x. And so we're starting with a function f again. And we know that it's sufficiently nice, continuously differentiable on some nice interval, right, say from a to b, and we're going to choose some x in between there. But now, whoops, I'm going to integrate not the function itself, but the arc length. I'm going to use the arc length formula. So what am I computing here? All right, so here's my y equals f of x. And here's a. Maybe here's b. And I choose some x in between a and b. What does this tell me? Yeah, right? If I put a b up here, this would tell me the arc length all the way from a to b. If I put an x in here, well, then this is telling me the arc length from a to x. So I actually can get a function, right? I tell you an x, and you can tell me the length from a to x. I give you another x, you tell me the length from a to there. Right? It's really the same process. Right? But by the fundamental theorem of calculus, then, I know the derivative of that function. Right? What's the derivative? So what's the derivative of this function? It's just this skit, right? Fundamental theorem says if you set up an integral like this and you take the derivative of that function, you just get this back. Right? So, in fact, so I actually have a little problem here the way I wrote this down because I have too many x's. Remember I put t's up here because I didn't want to, I can't really mix all those x's. So let me turn these into t's just for clarity. Right? So the derivative is the square root of 1 plus dy dt squared, right? It's just that middle function. That's by the fundamental theorem of calculus. Okay, let me go one step further with that. So, if I take s, right, what is ds? Well, ds is the derivative, right? Okay, we have this nice formula that tells us it's s prime times dx. Okay, this was how we worked with these differentials. But I know what s prime is. S prime is the square root of 1 plus, well, let me switch back to using an x here. dy dx squared times dx. Okay. Now let me square both sides. So I get ds squared equals this side squared. Of course, when I square this, I just have to square them individually and multiply. And when I square this, the square root just goes away. So I get 1 plus dy over dx squared, and then I get times dx squared. Okay. Now I multiply this dx squared in, and what do I get? ds squared equals, well, dx squared times 1 is dx squared, and dx squared times dy over dx squared is dy squared. And so you end up with this extremely elegant little formula, which looks a lot like what? Pythagorean theorem. So it suggests that we draw a picture. So let me draw a little piece of something. Okay, and let me start at one point. And well, remember, whenever we did this game, we can change the x, say, and that's delta x, which equals dx. Okay, we always could do that. And then the change in y is whatever was the corresponding change in the height of the function. Okay. But you could also draw the tangent line at the curve. And if you did that, then if you, instead of following the curve but followed this approximating tangent line, right, then you get this height over here. Right, and that height is dy. So you have a right triangle with base dx and height dy. So we know that the hypotenuse is what? Well, we know the square of the hypotenuse is dx squared plus dy squared. But we already know what that is. Dx squared plus dy squared is ds squared. So this hypotenuse of that triangle must be ds. So this is if you can remember this picture, you can actually recover this formula, right? Just by backtracking through these things a little bit. But I just think it's really nice that all these things end up really being the same idea. You really get to see the synergy between differentiation, integration, all the things we did last term, and all the stuff we've done with Riemann sums and definite integrals. Okay. Any questions at this point? Of course, any example I do from about this would just be the same thing, right? You have a function, you compute the derivative, you square it, add 1, take the square root, and now you've reduced yourself to an integrating problem. So since all that is what I would consider basic relative to this course, right? So not so many examples probably are needed. It's just a computational thing, really, right? Okay. So why don't we do some examples of areas between curves? Because I don't think we've gotten enough examples of that yet. All right, so I've cooked up a few. Let me start with an easy one. So let's find the area between the curves. Y equals x squared, and y equals the square root of x. So it's just a slight variation on the problem we did where we had y equals x. Now, when feasible, it's a good idea to draw a picture on these to help you out. So if we draw y equals x squared, well, we know somehow we only have to care about the positive side because the square root of x isn't even defined for negative x. So I don't worry about the left side of this picture. And then the square root of x looks like that. Okay, and so they've created this nice area in between these curves. Okay, so remember we have to do two things to set up the problem. We have to find out where they meet and who gets to be on top. So where do they meet? Well, what? Okay. They meet when x squared equals the square root of x. What, Dina? Ah, boy. Okay. So, of course, if we square both sides, we can get rid of the square root. So x to the fourth equals x. Subtract, and you get x to the fourth minus x equals 0. Factor out an x, and you get x times x cubed minus 1 equals 0. So x equals 0, and what's the other solution? X equals 1. Of course, you probably guessed that right from the beginning anyway. Yeah, most of the time, it's easy to guess when it's things so simple. Okay, fine. So that means that's 0, as we definitely knew, and this is 1. Okay, so that's 1. Now we know where they met. And now we need to figure out who gets to be on top. That's the question. Okay, so who's on top? Square root of x, right? He's the one on top. Okay. How do we know that? Well, we talked yesterday. We know that between 0 and 1, everything works backwards, right? A smaller power actually makes you bigger than a bigger power. Yeah, in this weird area, right, who gets to be on top is not determined by who's bigger, but who's smaller. So whichever is smaller goes second. Or I'm sorry, in this case, I mean smaller in this sense, right? The one who's bigger comes first, the one who's smaller comes second. Okay, and now this is just a computation. Yeah? Okay. Square root of x is x to the 1/2, right? By the power rule, we get 2/3 x to the 3/2. Right? Minus, okay, integral of x squared, 1/3 x cubed. Right? And we evaluate at 0 and 1. Of course, when we plug in 0, all these things are going to be 0. So we don't even have to do that. And when we plug in 1, we know all those are just going to be 1 and 1. And so you get 2/3 minus 1/3, which is 1/3, which is kind of a coincidence because that's what we got when we did it with y equals x squared and y equals x. Is that what we got when we did y equals x? Was it 1/3 or was it a sixth? A sixth. Yeah, so this is double that. Yeah, okay. That's nice. All right, let's do one a little more complicated, but the idea is still the same. I mean, the idea is always going to be the same until the next one where it's not the same. So, I don't want that. I think I need a lot of information on this one. Yeah. So let's go with, there's one function, x times e to the minus x squared. It's called upping the ante. The other function is going to be, I think I wanted x plus 1. Yeah. Right. Now I'm actually going to need some more info, and you'll see why in a second. So if I graph x plus 1, and I'm only putting on this side for a reason, but in principle I'd have to do more. So x plus 1, right, just starts at 1 and heads on up. Okay, and what about x times e to the minus x squared? How do we graph that? Well, we actually did graph that last term, I believe. One of the homeworks had something very similar to this. I mean, let's say we weren't in class, right, and you were just at home and somebody said, graph that thing. Yeah. Calculus. Oh, you're breaking my heart when you say that. We learned how to graph last term. Remember that? Yeah. Remember what Dai said? Dai said, no. First, a critical test. Then something, yeah. Must not be a very good mnemonic. Yeah. Okay, so go back and just take a peek at your notes from last term. Well, those of you who were here. Those of you who weren't, sorry, you lose. Okay, you can graph these sorts of things, right? Remember, of course, you can find little things like the domain and the y-intercepts and the x-intercepts. Then you look for symmetry and you look for vertical and horizontal asymptotes. Then you start taking derivatives, right? You can use the increasing-decreasing test, right? Then you do the critical points, right, where the derivative is 0 or doesn't exist, right? And that helps you find local maxes and local mins, right? Then you can use the concavity test, right? Okay, remember? First a critical test, then a cavity. Yeah, okay, so you can use a concavity test. That'll help you out. So you could graph this thing. Here's what we can do. We can just give a guess for the graph right now without doing all those things. Okay, so first, when x is 0, then that's going to go to 0. So we know we're going to start off at 0. Okay. So far, so good. No problems. Now, something else we know. As x goes to infinity, this thing is going to infinity, but then that minus sign makes it go to minus infinity. Yeah? Which means e to the minus x squared is going to what? It's going to 0, right? Because the exponent is going to minus infinity. Okay, so that's going down to 0. On the other hand, x is going up to infinity all the while. Right? So you got something pushing up and something pushing down. What pushes harder? Yeah, right? If you have a polynomial and an exponential, and they're both pushing in opposite directions, the exponential always wins. Okay? Polynomials grow slower than exponentials. Okay? So that means that this thing is pushing you to 0 as you go off to infinity. Okay? Even if that thing is going up. So we know that it's got to go down to infinity. Right? On the other hand, right, e to the minus x squared is always positive. Right? E to anything is always positive. And x, well, as long as you give positive x's, that's always positive. So this thing, right, or it could be, it's 1 point at 0, but as soon as you put in positive x's, this thing's got to go up. Okay? But we also know once it goes up, it's got to go down, because it's got to eventually tail off to 0. So this thing has to look something like that. So there's the question, right? I drew it so that they didn't intersect. Shouldn't they intersect? Okay, and this, right? Well, you have to make an argument, and of course you could use this with calculus. All right, using your derivatives, you could figure out what the maximum is. Right? Find this local max. Take a derivative, set it equal to 0, find the point where you get a local max, and then evaluate and see what that max is. Right? And then you can determine, does this thing ever actually cross that line? Right? Or even better is if you see that this max isn't too big, right? If it's already smaller than 1 or something, then you're golden. Right? It could actually cross before it hits the max, in fact. So, okay, then you got to see, okay, subtract these two or something, see that it's not 0. But it's not that hard. It just takes a little bit of effort. Okay, so if they don't intersect, I can't very well ask you for the area between them, can I? Doesn't make any sense, right? Of course, it's just a lot of area. Okay, so I have to give you more information. So first, all right, I'm starting at x equals 0. I don't care about things on the negative right now. And second, I'm only going to go between up to 2. Right? So, well, I don't know where that is vis-a-vis the maximum. We could figure that out with the derivative. So I'll just draw it roughly around here. Okay. And now I have a region. Okay, I can try to find this area. Okay, that's messed up. Okay, fine. If I want the area, I just set up the integral. Okay. It's going to go from, well, when x equals 0 to x equals 2. Okay. Now, if I want to know who comes first, I've got to find out who's on top. Okay, so who's on top? Right, x plus 1. Minus xe to the minus x squared dx. Okay, so now you get to integrate. Right? Of course, it looks bad at first, but then you think, wait a second. That's just an x. That's just a 1. And, well, let's worry about that in a second. Okay? So let me solve this integral without the limits at first. Okay? Then we'll put them back in at the end. So let's just start with this. Okay, solve this antiderivative. So, well, it's easy the first couple, right? I just, okay, that's a half x squared plus x. Minus, okay, now I got to actually do something. Okay, so I actually have to compute this integral. Okay, so let's compute this integral over here. What is a good idea for this one? I'm hearing good ideas. Parts or substitution? Okay, so there is disagreement. This is good. Okay, now if you want to use parts, but you could also use substitution, which should you try first? Substitution, right? This is usually the easier method. Okay, so maybe parts is the right answer, but we're going to try the substitution first. Okay, so what would be our substitution? U equals. Okay, so I've heard negative x squared and e to the negative x squared. Negative x squared, that's the consensus. Okay, now why? Well, if we made an e to the negative x squared, when we differentiate, we still are going to get this nasty e sitting around. ln e? You mean ln of what? Of this? Uh-huh. Oh, then you want to do ln of it. Well, this sounds like a lot of work. It's not. It sounds like more work. Okay, well, let's try it in a second. We'll see. Okay, so here, du is minus 2x dx. Okay, and look at that. The x and the dx are going to go away as long as you can somehow get rid of this minus 2. Yeah? Okay, but I'll just put a minus 1/2 out here, and that'll clean things up. So this is -1/2 integral of e to the u du. Okay, now this is very easy. This is -1/2 e to the u, but u is -x squared. Now, how in the world could the other way be less work than that? You gotta. It's the same? Okay, let's try it. So e equals -x squared. Okay, now I do another one. Okay, so ln of u equals -x squared. That's true. Okay, and then 1/u du equals -2x dx. Right? How in the world is this less work? No, I mean it's just a little more work. You're, I mean, yeah, I guess you can probably get away with this, but it's going to be a pain. I mean, it's not a pain. I mean, it just is what it is. In the end, you'll just have to. It's like, you know what it is? It's like instead of walking to the door, you first walk over to Chris first, and then you walk over to the door. It's superfluous, right? Why would you ever walk over to see Chris? I'm just kidding. I'm just kidding. I meant Lath. Okay, so let's see. So we now have the antiderivative. It was 1/2 x squared plus x minus, so plus 1/2 e to the minus x squared plus c. Okay. Now, when we go back in, we don't need to worry about the plus c, because we can take any antiderivative we want. So I just take the one where c is 0. So this becomes 1/2 x squared plus x plus 1/2 e to the minus x squared, evaluated at 0 and 2. Okay, we put in 2. We're going to get, okay, 2 squared is 4, times 1/2 is 2, plus 2 is 6. So 6 plus 1/2 e to the minus 4. Minus, and then we put in a 0. And when we put in a 0, the first two terms go away. Then you get e to the 0, which is 1. So then you get minus 1/2. I think there's a mistake in here somewhere. Okay, but if this was correct, then you'd get 6 minus 1/2, which is 11/2, plus 1/2 e to the minus 4, so 11 plus e to the minus 4 over 2. I think that should, when I worked it out earlier, it was a 7, I think. So there must be a little, oh, this was a 4. There we go. There we go. So now it's 7/2. Good. Good, 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 good. Excellent. Well, it's okay. 2 squared is 4. Divided by 2 is 2. Plus 2 is 4. Somehow I didn't divide it. Go back on the tape. You'll hear me say, divided by 2 is 4. Plus 2 is 6. Something like that. Okay. So that's the area. 7 plus e to the minus 4 over 2. Not bad. Yeah. It's the first answer that's somewhat not nice. What's that? Yeah, probably, you know. But, I mean, here's the thing, right? All this problem is setting it up. After that, you're back to an integral problem. And somehow that's the goal. Every time you get a new problem in mathematics, what you want to do is find some short transformation that will turn it into a problem you already know how to solve, like an integral problem. You mean of this? No, because here we've done a definite integral, right? So we've had to plug numbers in. But if we took this, the indefinite integral, and you integrated and you differentiated it, you should get back x plus 1 minus x e to the minus x squared. Right? Which works, right? Because the derivative of that is x, 1, x e to the minus x squared. I mean, we constructed it to work, so it's not surprising. well, I mean, 0 is always a nice choice, but yeah, effectively randomly. Right? There was nothing about these functions that told me I had to choose 0 or 2. I just all that these functions told me is that I had to choose a beginning point and an ending point because they weren't intersecting. Right? At least over here. Right? Now, when you put in negative x's, then maybe, well, let's see, what's going to happen? That'll actually go down, and it's possible these things are going to intersect. Right? In fact, very likely they'll intersect. Very, very likely they'll intersect. Okay. So if you went over here, you could probably at least get rid of one of these things. But they're not going to intersect twice. Okay. One last point that I want to give you. So you know they're always talking about how we are biased by living in Western society, and that shapes the way we think. No? Okay. So there's a lot of truth to this. That's fine, and it happens in mathematics too. We are biased by living in y is a variable dependent on x society. Yeah? We are not happy when we see things like this. Right? We say, well, that's not a function. It's just garbage, right? I mean, and all it is, really, I just took a parabola and I turned my head, That's all it is. You should be able to say something about these sort of situations, right? If I just turn this 90 degrees, y equals x squared. What? No big deal. If I turn it like this, and all of a sudden it's like, I don't know what to do. You know you said that to me. I'm just kidding. Okay, so let me write down a problem. And let's see, x, y plus 1. Let me write down something just to be annoying. Yeah? Make you feel good? Yeah? Nice? Try to graph those suckers? What's that? No problemo. That sounds like a volunteer. Okay, now let's see here. Well, if one way to do this is to just turn yourself, right? Make everything look like it should. You say, okay, minus 3, that's going to take y squared and it's going to shift it down 3, which means to the left. 1, 2, 3. And then, well, that half is just going to squeeze it a little bit, so we don't even worry about that when we graph it. Okay, that should be symmetric about the middle, but it's not, but we don't worry. And then y equals x equals y plus 1. Okay, so that should be a line that goes like this. All right, or no, like this, because it's supposed to be, if x equals y, then y equals x. But then it's got to shift it by 1. Of course, that would actually be the same thing as y equals x minus 1, so I could actually just shift it down by 1. Right, and you get something like that, and something like that. Right. And if I want the region bounded by these, I now get this piece. Okay, so if I wanted to compute this area, I could solve this for y. Right? I could try to anyway. It would work. You'd have this little problem with this plus or minus business coming from when you took the square root. Right? So you'd actually be kind of annoying. But then something really weird would happen. You'd have to think about, which is the top and bottom function. That's kind of weird here. I mean, this is over that, but that's the same part of the function, right? I mean, there's something strange going on there. Okay. But if we dropped our way of thinking that it always has to be y as a function of x, and we just said, well, let y not be a function of x, but x be a function of y, and we just turn our head like this, right, or even like this, or like, yeah, which one should be on top? Right? Well, these are the, you can think the positive values going this way, and these are the negative values going that way. So that should be on top of that. And if you turn your head like that, you see, yeah, sure enough, this is on top of that. So if you're defining your functions, right, in this way, then it's not top over bottom, but right over left. Okay? And we can set everything up the same way. Right? We set up an integral. Well, okay, we need to figure out, right, where we're going from. Right? We're going from here to here. We need to know what those limits are. Okay? Well, we haven't done that yet. But assuming we figure out what those are, then we just need to put our top function, which is the right one, which is y plus 1, and we have to subtract our bottom function. And now when we integrate, we're not integrating with respect to x anymore. We're integrating with respect to y. Yes. Right? We need the y coordinates, not the x's. Exactly. Okay, so how do we get the y's? Well, we want to know when these two things are equal. So we set them equal to each other. So we have, okay, a half y squared minus 3 equals y plus 1. All right, and so we say, okay, fine, let me subtract everything over. Half y squared minus y minus 4 equals 0. And if we multiply everything by 2, it's probably easier to see what this is. Y squared minus 2y minus 8 equals 0. Okay. Can we factor that thing? Yeah, let's see. We'll use a plus 2 and we'll use a minus 4. Very good. So y equals minus 2 or y equals 4. Okay, and so, okay, let's see. That must be the minus 2. And this must be the 4. Whoops. That must be the 4. Okay, so we're going from minus 2 to 4. Okay. And, well, now this is a reasonably easy problem. Yep. So this ability to turn our heads 90 degrees, or pi over 2, as I tell my son, who is going to be the youngest in the first in his class to know what radian measure is. This is always good, you know. Let me tell you something about radian measure. That is not dependent on your culture. Degrees, right? This is completely dependent on our insistence on having 360 degrees in a circle. Right? Radian measure, this goes across cultures. Every alien race that we would meet would know radian measure. No? Absolutely. Whenever you meet an alien, say, tell you something about radian measure. Now, but we're going to need this later on when we start doing volume problems. Because sometimes when we do our volume problems, right, it's going to be just easier to view everything, right, in terms of y's instead of our x's. Right? So we're going to need to learn to turn our heads. Okay. And so then it's, we no longer get to ask, who's on top, but who's on right. So, okay.